My name is Chase Gibson. I'm a technical sales specialist with Mori Microwave, and today we're going to take a look at how we can eliminate measurement inconsistencies and increase confidence in your measurements. But first, let me ask you a few questions to see if you can relate to one of the following scenarios. Have you ever measured the same device twice only to get different results? Or in a similar case, measure the same device on two different systems with different results? Perhaps even worse, have you ever shipped a product to a customer only to have them inform you that the performance they measured does not agree with the performance you measured and reported? Now let me ask you again, can you relate to any of the above scenarios? How much time and money has this cost you, and what damage has this done to your relationships? Let me jump right into explaining how Mori can help you to eliminate these above issues. In front of me, I have a typical S-parameter measurement system comprising of a VNA calibration kit, cable assembly, and device under test to measure. This is likely similar to what you have in your lab. The only difference is that my system is being driven by Mori Microwave's Insight software platform. Insight is the industry's first commercial VNA calibration, validation, and S-parameter measurement software compatible with most commercial VNAs that is designed to characterize each component of a measurement setup and quantify its error contribution on a DUT measurement. It's the individual error contributions that add together to create those inconsistencies, and by characterizing, quantifying, and then reducing those errors, we're able to ensure accurate and repeatable measurements regardless of the measurement system, location, or who is measuring the DUT. Now let's take a look at how Insight characterizes each component, quantifies the error as measurement uncertainties, and helps you gain confidence in your measurements. Now let's get started. Today's demonstration will concentrate on characterizing each component of a measurement setup and quantifying their error contribution or uncertainty on a DUT measurement. Characterizing components starts with the Configure, Library, and Settings module. In this section, users can create a database of available system components, including VNAs, calcuts, cable assemblies, connectors, and probes. Starting with the VNA tab, users can define available VNAs by adding a unique name, selecting the appropriate instrument driver, and setting the GPIB or LAN address. Once that's done, it's time to characterize the VNA's possible error contributions or uncertainty by clicking on the Characterize button. As you can see, Insight runs two different tests, noise and drift. The noise test takes around 1 day, and it's the same for the drift test. Since each test takes over 24 hours to properly characterize the contribution, I'll walk through the menus but will skip the test and recall the data I took prior to this demo. Next up is calcuts. Similar to VNAs, users can define available calcuts by adding a unique name, identifying the connector type, and then the gender of the kit. This is also where we will load the calcut definitions, either choosing a generalized polynomial file or a unique set of characterized measurement data for each calibration standard. Mori supplies its characterize or CD calibration kits with characterized uncertainty for each calibration standard, and it's this uncertainty that will carry through to the S-parameter measurements. Now we get to the most critical components with regards to potential sources of inconsistencies: cables, connectors, and probes. With cables, it is often the change in electrical performance with movement or flexure that impacts measurement consistency. Insight characterizes the change by guiding users through multiple movements over the actual motion range of their test setup, measuring multiple times and creating an error or uncertainty model. This takes into account both transmission and reflection measurements of the cable. For the cable transmission test, it's just a matter of calibrating the VNA, connecting a short to the end of a cable, and then moving the cable based on your typical application. For the sake of time, I'll just run 3 iterations out of the 9. Now that the cable transmission test is over, I'll start the cable reflection test, which will be the same process as the cable transmission test, but with a load connected instead of a short. Again, for the sake of time, I'll just run 3 iterations. After the cable has been characterized for both transmission and reflection, I'll jump right into connectors and probes. With regards to the next 2 tabs, errors or uncertainty come from the connection repeatability. For connectorized applications, this can be due to connector concentricity, pin depth, or the user not applying the same connection torque each time. For probes, this is the variation of contact over multiple touchdowns. Since I'll be using a coaxial connection, I'll just walk through 2 iterations of connector repeatability. Now that I've characterized the uncertainty contribution of each of our measurement setup components, it's time to calibrate, validate, and measure. I'll go through those steps in future videos, but for now, I'm going to hop right into an example measurement. This is where I'll show the S parameters reported by the VNA as a line, but also the potential errors or uncertainty region contributed by each component of the system, as well as the component's individual percentage of contribution. In reality, your measurements are not aligned, but rather a region of possibilities. That means that the actual performance of the DUT can be anywhere in this region. In this example, less than 6% was contributed by the VNA, 10% by the calcutt, around 84% by the cable, and less than 2% by the connector. This region of uncertainty can be reduced by improving the maximum contribution of each piece of equipment in the system setup. As I showed in the demonstration, your measurement isn't a line, it's a region. Measurement inconsistencies over time from system to system, from location to location, and from user to user can often be traced back to the measurement errors or uncertainties of each individual system. By characterizing each component of a measurement system, we are able to identify the contributions of uncertainty and concentrate our efforts on eliminating the primary impacts of measurement inconsistencies. We can also have faith that our measurements are substantiated, and as long as multiple sets of measurements fall within the same uncertainty boundaries, they are all accurate. Increase confidence in your measurements, save time and money, and increase customer satisfaction by using Insight. For more information, visit morimw.com. Thanks for tuning in.